So again, we're determining whether a sequence will converge or diverge in this video. So the first sequence I want to give you or share with you is an equals 9 to the n power over 5 to the n. So first thing that you can do with this problem is that you can rewrite it as follows. Since both 9 and 5 are raised to the n power, you can rewrite it where you look at it as a fraction, as a ratio, 9 over 5, all of that is being raised to the power of n. Now, this is helpful because when you look at this, what does this sequence look like to you? Say it again. Yeah, it sort of looks geometric, right? And one thing about geometric, they're usually in the form of like a times r to the n, and then so forth, right? So in this problem, our a, well, the coefficient will be just 1, okay? But you could identify your r value. What is your value of r? 9 over 5. And if you look at the absolute value of r, or the absolute value of 9 over 5, is this going to be less than 1 or greater or equal to 1? Yeah, it's going to be greater or equal to 1. So what does this imply? Since the absolute value of r is greater or equal to 1, then the sequence diverge. Okay. If r, by the way, was the absolute value of r was strictly less than 1, then it will converge, and then we can figure out what it converges to, right? I'll have another example of that coming later. But for now, we just want to determine whether the sequence converges or diverges. In this case, it diverges. Another thing that you can make a note of is that, right, here's just a note, is that if you look at the limit as n approaches infinity of 9 over 5 to the n power, this limit is equal to what? Is equal to infinity. Now, because it equals to infinity, is infinity a real number? Is it a real number? It's not a finite, it's not a single real number. So this limit essentially diverge, right? So since an, the sequence, will approach infinity, then an diverges. Your sequence will only converge if it's approaching a real number, okay? A single real number. So that's my first example. Let's look at a second example, actually. Example number 2. So in example number 2, we have the limit, sorry, not limit. We have first the sequence, Bn equals 6 minus 2n squared over n squared minus 6. So if I compute a limit here for this example, the limit as n approaches infinity of Bn, if this limit approaches infinity or negative infinity, or has some sort of alternating behavior, then it will diverge, right? But if it approaches a single real number, when I compute this limit, then we can say that it converges, right? It will converge to whatever we get. So since Bn was defined as 6 minus 2n squared over n squared minus 6, then that's the limit as n approaches infinity of what I'm computing. Now, to help you out a little bit, just to show you all the properties of limits that's happening here, since I have a difference of 2 terms, 6 is considered a single term, and then the 2n squared over n squared minus 6 can be considered another term. You can split this into 2 limits. You'll get the limit as n approaches infinity of 6 minus the limit as n approaches infinity of 2n squared over n squared minus 6. Now, what do you think will be the limit as n approaches infinity of the number 6? That's going to be 6. if I look at the limit as n approaches infinity of 2n squared over n squared minus 6, that limit should be approaching what number? That number should be approaching 2. How can I tell? Well, since the powers are the same, then you take the ratio of their leading coefficients. So 2 over 1 is just 2. Okay, so if we do the difference, the subtraction, we get 6 minus 2 is 4, right? So we can make a note. That's our answer. But we can say that our Bn, the sequence Bn, converges to 4. And you can look at that term by term if you wanted to. All right. Let's look at a couple more examples, I guess. I think I could do 2 more examples in this video. Here's example 3. Let's say I have Cn is equal to 8 plus negative 2 to the n power. To really understand what's happening in this sequence, what you'll need to do is look at it term by term for this example, right? So to approach this problem, let's look at term by term, okay? So let's actually compute a few sequence values, right? Let's try to compute C1, C2, C3, C4, C5, and C6. Now let's try to establish something here with this, okay? So if I compute C1, C2, C3, C4, C5, and C6, then that's basically plugging in those numbers 1 through 6 for your value of n. So you're gonna get 8 plus negative 2 to the first, 8 plus negative 2 squared, 8 plus negative 2 to the third, 8 plus negative 2 to the fourth, 8 plus negative 2 to the fifth, and 8 plus negative 2 to the sixth. Oops, there you go, 6. All right, so the first one is going to be 8 minus 2, since negative 2 to the first is negative. So you have 8 minus 2, which is 6. If I do negative 2 squared, however, what would that be? 4. So this will give us 8 plus 4, which is 12. All right, if I do 8 plus negative 2 to the third, that will be 8 minus 8, right? Because the power is odd, right? For your odd powers, you're going to get these negative numbers. So you're going to get what? 0. Then we have an even power. So for the even powers, you should recognize that it's going to be positive. So what's negative 2 to the fourth? 16. So this gives us 8 plus 16. Now, what is 8 plus 16? 24. Okay. Here we have negative 2 to the fifth. So what's negative 2 to the fifth? Negative what? Negative 32. This becomes minus. So this becomes negative 24. And then the last one that I have so far, you could have kept going if you wanted to. Oh, sorry. There goes my color code. What's negative 2 to the 6? 64. So 8 plus 64 is 72. Is there any sort of pattern that you're recognizing? Like, meaning when you look at these sequential terms, right, you have Cn is equal to, well, the first term was 6, second term was 12, third term was 0, fourth term was 24, fifth term was negative 24, the sixth term was 72, and it keeps going on and on. What do you recognize? Is it approaching a single number? No, it doesn't look like it's approaching any number at all. And we can see that that's actually true. So what we have here in this example is that the limit as n approaches infinity of Cn, it unfortunately does not exist. This is a case where it doesn't go to infinity, it doesn't go to negative infinity, it simply does not exist. So because it does not exist, then our sequence Cn diverges. All right. Now, the rationale behind this, right? The reasoning or rationale to this is the following. Notice the pattern again that we saw. What happened when the power was odd, or when the value of n was odd? As that's right. So the rationale is that as n is equal to an odd number, and the sequence terms for Cn is going to negative infinity, right? If you look back, first term was 6, the third term was 0, the fifth term was negative 24. So that indicates that when n is odd and it's still going up, right? 1, 3, 5, 7, 9, and so forth, the sequential terms and the odd positions are going to negative infinity. On the other hand, as n is equal to an even power, and approaching infinity, so I'm going to use an arrow for approaching infinity, then what happens to the sequential terms for Cn? Look at these terms, all the terms that are in the even positions. You have 12, 24, 72. This will be approaching infinity. Now, is infinity and infinity the same thing? Infinity and negative infinity. No, they're not. They're not the same thing. So they're not equal to each other. Any questions?
So, like, if any other way to say this question is going to be like low and sometimes.
Yeah, this is an example where it's best to look at it term by term. Okay. The other two examples, we could have somehow do it term by term as well, but using some methods that we learned so far in Calc 2, like the geometric, the things with R, or computing a limit as n approaches infinity, it, it makes our solution stronger, essentially. This was an example where I can't necessarily compute I couldn't necessarily compute the limit here. I mean, okay, let's say n was going to infinity. As n is going to infinity there, the -2 is either going to become a positive number or a negative number. And when you add 8 to it, is either going to decrease or increase, right? If it's even, it's increasing. If it's negative, it's decreasing. So this was an example where I had no other choice but to look term by term. Okay. All right. There's just one more example I want to show you, another method for computing a sequence. No, because this is not a series. You could use it as long as it's an alternating, but this is not a, sorry, this is an alternating sequence, but not an alternating series. So I can't use that. They're wrong. Nope. All right. One more example number 4. Let's say I have dn is equal to cosine of n plus 6 over n. So let's make a note. First, look at cosine. As n is approaching infinity, cosine of n, what do you know about it? What will be your solution as n approaches infinity for cosine of n? That's right. It's going to be, it's bounded between -1 and +1, right? So cosine of n is bounded between -1 and 2, or and, I'll put and instead, -1 and 1. Okay, so mathematically, this means that -1 is less than or equal to cosine of n, which is less than or equal to 1. Now, why did I write it in such manner? The reason why I'm writing it in such manner is because essentially what I want to do is replace this cosine of n with d of n. And in order for me to do it, I have to, whatever I do in the middle, essentially, I got to make sure I do it to both sides of the inequality or the endpoints of your inequality, right? For example, because I have a +6 attached to cosine of n in the sequence, if I add 6 to cosine, then I have to add 6 to the endpoints. All right. So again, if I originally added 6 to my cosine of n, then I have to add 6 to the endpoints. Now, there's another thing that I could do as well. If you look at the sequence dn, in the denominator, there was a n there. So mathematically, if I divide the middle by n to mimic d of n, then I have to divide the endpoints by n as well. Okay, now let's just rewrite this. What we have now is that the middle given sequence, and it's trapped essentially by two other sequence. The two sequence where it's trapped, where it's basically trapped. The first one will be -1 plus 6, which is 5. So this will be 5 over n. And the last one will be 7 over n. Okay, so what I can do is apply the squeeze theorem. Sorry, it looks a little glitchy. I don't know why. All right, so if we apply the squeeze theorem, you're essentially computing the limit as n approaches infinity of 5 over n, and you're computing the limit as n approaches infinity of 7 over n. So what are these limits equal to? Both of these limits will be equal to 0 as n goes to infinity. So therefore, by the squeeze theorem, we'll have that the limit as n approaches infinity of cosine of n plus 6 over n is going to equal to 0. That's right. And that's how you apply the squeeze theorem there. Okay. So sometimes you got to check whether or not you have something that's a little bit bounded above and below. Like, for example, cosine of n was bounded from -1 to 1. Therefore, cosine of n plus 6 would be technically bounded between 5 and 7. And then you just divided everything by n. Compute the limit of the endpoints, 5 over n and 7 over n. As n goes to infinity, you get zeros. So because those two are the same thing, then by the squeeze theorem, the middle also goes to 0. And that's it.